This is an exciting moment for me because this is the last thing that I have to record for MA 266 ever. I just finished, ironically, the topic video for separation of variables, which, is the thing we started out with in the course, and now I'm doing the most recent final, which is by far the hardest final that we've had in recent time, just like the fall 2019 final was the hardest for MA 265. But that slip of the tongue will show you something silly here. They mislabeled their answer key. If you go click on the fall 2019 answer key for MA 266, you get something that says spring, but all of these are correct for fall. Freaked me out a little bit. But let's get going. Number one, this field is the slope field for which differential equation? So we see at y equals 3, y prime is equal to 0, and at y is equal to 0, y prime is equal to infinity. So we should have undefined behavior there. What else? What else do we know here? Okay, well, we know that we should be dividing by y so that y is equal to 0 gives us this infinite slope there. And all of our answer choices do that. So we're not too worried. We're not too worried about that. But importantly, because our slope is positive before 0 and positive after 0, I know for a fact that whatever is leading to 0 creating this behavior has to be squared, and I'll show you why. So that actually brings it all the way down to E or C, because for this squared term, while we are between -3 and 0, so let's say -1, if we plug in -1 to C, we will get a positive number times a positive number over something that's always positive. And if we go up above 0 to say y equals 1, we'll have positive times positive over another positive. If this thing was not squared, we would get a negative slope for this area in here between -3 and 0. So that is no good right there. And speaking of which, I'm pretty sure C will act exactly the way that we want it to in all other ways. Oh, and I kind of forgot to mention, we do also have down here that y equals -5 is a solution for y prime equals 0. So that is good. And I know for a fact also, kind of by the same argument, that E is not a solution, because this y plus 5 squared term should be semi-stable, just like 0 is. And we see that, in fact, it is not. It is unstable. We have solutions flowing away from it on both sides. So that leaves us with C, and you can go through and check yourself its behavior for 1, 2, 3, 4, all 4 of the domains that we really care about. So 1 is C. 2, let's find the number of stable critical points for this autonomous equation. So remember what I was saying, if we have anything that's squared in here, 1, we don't really have to care about it at all because it'll always be positive. It's never going to change the value of our derivative. And as a result, around that point, so around x equals 1, it will either, the flow will be either going up to it on one side and away from it on the other, or the other way, just because, like I just said, this root will never change the sign of our overall equation. So it's always semi-stable, so we know that we can just cross this guy out completely and kind of pretend it doesn't exist, and it simplifies our calculations slightly. So now we're left with roots of -3, -2, 0, and 2. So we got to check all of these. If we plug in -4, we will get a times a negative times a positive, so we'll get an upward slope there. And then between negative 3 and negative 2, if we plug in negative 2.5, we'll get a negative times a positive times a positive, so there's negative slope down to 3 from 2. What if we plug in negative 1? We'll get negative 1 multiplied by a positive value, and then multiplied by a negative value. So there we go. And also, I'll go as we go. I'll circle the stable points that we're getting. We found one stable, one unstable so far. And then if we plug in x is equal to 1, we'll get 1 times, so a positive number times a positive number times a negative number. There we go. And we are actually completely done, because it doesn't matter what behavior we have around 2. If it flows towards it, it's semi-stable. If it flows away from it, it's unstable. So we always will only have these two stable critical points. Let's find the explicit solution for this initial value problem. Let's divide y squared out and replace our y prime with a dy dx. So 1 over y squared dy is equal to, multiplying that dx over x squared plus 1 dx. Integrating both sides, negative 1 over y is equal to, what is this, 1/2 ln x squared plus 1, plus c. Looks good to me. Let's solve for this value of c, given that y at 0 is 3. So negative 1 over 3 is equal to 1/2 ln of 1, so that's 0, and this is just equal to c. So c is negative 1/3, like that. We can flip the signs on all of our terms here, and then flip the numerator and denominator of both sides, and we'll see that y is equal to 1 over, and I'll write this the way that they do, 1/3 minus 1/2 ln x squared plus 1, and then they mess with things a little bit, multiplying the top and the bottom by 6, so 2 and 3 there, which leads us to B for number 3. They did this to us on, what was it, the first midterm last semester in Calc 3, where they just threw what really seemed to be a Physics 172 question at us, which is not too bad, and I'm not complaining because this one's pretty easy. We have a stone dropped from rest from an initial height of 25 feet, and it's falling, and the only issue is that it's falling using the metric system. Wait, that's the other way around. Whatever we use, imperial units, yeah. Wait, the U.S. units, yeah, and that's my only issue with it. But this should be pretty easy to compute, because a is equal to negative g, where g is 32. That's our acceleration. Integrating a, we'll see that v is equal to negative 32t plus c, but since we know that it's starting at rest, from rest, there we go, we know that its initial velocity is 0, so we can get rid of that c term. Integrating v for position, that is negative 16t squared plus c, where this initial position is 25 feet. And we're solving this for p is equal to 0, we're solving it for t. So we can say that 16t squared is equal to 25, or t is equal to plus or minus 5 over 4, but we're not having negative time, so 5 over 4 seconds is our answer. We strike the ground at 1.25 seconds, which is E. We have an exact equation. Fun fact, whenever they give you this whole select not exact kind of thing, it's never been that. It's always exact. Leave it to them to do that to us this time around, though. So we know that we can call this portion of our equation M, and this portion that's multiplied by y prime n. And if my is equal to nx, then our equation is exact. This is because our solution, the implicit form of our solution, should be, I'll call it some function phi of, oh no, pencil's starting to act up, some phi of xy, where phi x, the partial derivative of phi with respect to x, is m, and phi y is n. Thus, we know from Calc 3 that the mixed partial derivative, phi yx, should be equal to phi xy. And so my is really this mixed partial derivative, and nx is really this mixed partial derivative. So if we can solve it exactly, this should be true. So finding my, we get 1 over x plus 6, and then nx gives us 1 over x, oh, my. Yeah, I thought I had it. Yeah, my, okay, so my is equal to nx, so our equation up here is exact. That means we can find the integral of m dx, y over x plus 6x. That's because we know that, okay. I'm misleading myself with these over here. We know that m is the partial derivative of phi with respect to x, so we're integrating that dx, and then we're comparing that with the integral of n dy, which is ln x minus 2y dy. This will give us y ln x plus 3x squared, and over here we get y ln x minus y squared. So noting that we have a repeat here, we're only going to count that once, and we're going to count everything else, and all the unique bits, once each. So we can say that y ln x plus 3x squared minus y squared is equal to some constant c. And so now we have the implicit form of our solution. And if you want to go and prove to yourself that this is in fact the function phi that satisfies everything that we've been talking about, take its partial derivative with respect to x, you will get m, and take its partial derivative with respect to y, and you will get n. Since y at 1 is equal to 2, we can say that c is -1. Sorry, I did that in my head, but this will go to 0. This is 3 minus 4, so we get -1, and D is our answer for 5. The solution to this thing is given by what? Okay, this killed me on the real exam. When I took it for the first time, like under real conditions, blah, 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 I actually recorded and uploaded it if you want to watch the pain. The first time through, I did what any sane person would do and tried to solve this using v equals y over x, and dy dx is equal to dv dx times x plus v, like how you normally would when we see both a rational expression in here and literally x plus y just sitting there. And so imagine my surprise when this thing's exact. And the only reason I figured out that it was exact is that I looked at the answer choices, and these are very exact looking answers to C. And so we should be able to do this. What we're looking for is to get it into the form where we have some function times y plus some function times y prime, that's n, and some function of xy times 1. So let's set that up. Let's subtract this back over onto this side. And, oh no, I actually don't want to do that. I want to multiply x squared y over. So x squared y times y prime, and I'll order it the way I'm used to, plus, it's late, xy squared is equal to 2. So we can subtract this 2 And there we go. We have our function n and our function m. If we take my, we get 2xy, and if we take nx, we get 2xy. This was a pretty cool moment having that actually work out. I was a little bit too proud of myself, but this is midterm 1 material, so maybe I shouldn't have been. But either way, hard question. So what we can do now, just like in the last question, we can take the integral of, I'll mark these m, n. We can take the integral of m dx, and that'll just give us x squared y squared over 2 minus 2x, and then this integral here will give us, we're comparing that with x squared y squared over 2. And so what they do here is take this guy, which, you know, we see the overlap here, so we write as our solution x squared y squared over 2 only once, minus 2x is equal to c. They multiply everything by 2 and just use a c that is 2 times our old c. And as a result, we land on D for 6. 7, let's use Euler's method with a step size of h equals 1 to find the approximate value of y equals 3. So we can take y at 0 equals negative 8 as our first condition and use that to approximate y at 1. That will be approximately equal to, there we go, y at 0, which was negative 8, plus our step size multiplied by y prime evaluated at this condition here. That will be negative 4, so we get negative 12. So y at 1 is approximately negative 12. Y at 2, on the other hand, is going to be y at 1, so negative 12, plus 1, multiplied by y prime evaluated at this condition now, the most recent one that we've computed. That will be 1 minus 6, so negative 5. So we get y at 2 is approximately negative 17. Y at 3, following the same process, is negative 17 plus 1 multiplied by 2 minus 17 over 2. And 17 over 2 is 8.5. So this is negative 6.5. And negative 17 minus 6.5 is negative 23.5. So 7 is E. 8, we're finding the solution to this initial value problem and computing y at pi. We're just solving our characteristic equation here, so r cubed plus r is equal to 0. R times r squared plus 1 is equal to 0. So r is equal to 0 and plus or minus I. So we can write yc as c1 plus c2 cosine t plus c2 sine t, and we can write y prime as negative c2 sine of t plus c2 cosine of t. And it looks like, yeah, we're going to have to take a second derivative too. Y double prime for our characteristic solution will be negative c2 cosine t plus, nope, not plus, minus c2 sine of t. So we can make a nice matrix out of this with our initial conditions. Y at 0 will be 1c1 plus 1c2 plus 0c3s is equal to 2. Y prime, and I'll fill in these 1 and 1. Y prime will be 0c1 minus 0c2 plus 1. Sorry, I wrote, whoa, that's so weird. I think I did exactly the same thing where I wrote 2c2s the last time I took this exam. I usually don't make that mistake. Yeah, 1c1 is equal to 1. And then for y double prime, we will get 0c1 minus 1c2 plus 0 C3, because we're evaluating that sign at 0, is equal to that right there. So we can simplify this down by adding row 3 to row 1, like so. And so we can take our YC and replace C1 with 3, C2 with -1, and C3 with 1. We're evaluating y at pi, so that will be y at pi is equal to 3 minus -1, so plus 1, and then the sign of pi is just 0, so 4 is our answer, A for 8. We have a mass spring system with an external force, and we're finding the particular solution obtained by undetermined coefficients, and we're evaluating it at pi over 4. So let's get going. We have to make sure that the guess that we would make for our particular solution, which we would like that to be a cosine 2t plus b sine 2t. We have to make sure that plus or minus 2i is not a solution for our characteristic equation here. So r squared plus r squared plus r plus 1 is equal to 0. Nah. Look at that thing. That's not working. We could plug 2i in, but I know for a fact that ain't factoring the way we want it to. And even if it does have 2i as a component, it will have e to the something t additionally attached to it. So that's no good, and so we don't have to worry, which is nice, because taking those derivatives when we have like when our guess is t sine t plus t cosine t, I have nightmares about that. So y prime pg of t is equal to negative 2a sine t plus 2b cosine t, and y double prime is negative 2a cosine t, nope, not 2, negative 4, and minus 4b sine t. So now plugging these in, and I'm going to, oh no, that's why I messed that up. I started writing t instead of 2t. There we go. So when I plug everything in, I'm not going to be writing the cosines and the sines because I don't want to write 7 of them. And I'm just going to put c and s instead, because at this point it doesn't matter. We're not evaluating anything in particular yet. So y double prime will be minus 4a cosine minus 4b sine plus y prime, so that's minus 2a sine plus 2b cosine plus y, so plus a cosine plus b sine is equal to negative 13 sine. Great, let's make a matrix. We got to make some equations first. Pulling out all of our cosines, we see that negative 4a plus 2b plus a is equal to 0. So overall, negative 3a plus 2b is equal to 0. And then pulling out our sines, negative 4b minus 2a plus b is equal to negative 13. So this plus b will turn this into a negative 3, and we can make a matrix. We have negative 3a, 2b is equal to 0. Got to be careful here. Our negative 2a will come first, so negative 2a minus 3b is equal to negative 13. Let's simplify this. Let's multiply row 2 by 3, and also multiply by negative 3. That will give us 6, 9, and 39 there, and then we still have our negative 3 to 0, and then we'll add 2 row 1s to it. That'll give us 0, 13. Oh, look how that works out. We get 1, and 3 there, 0, -6 there, so 1 and 2. So that lets us go back and rewrite our yp of t, because we know a is 2, so 2 cosine 2t, and then b is 3, so plus 3 sine 2t. We're evaluating this at pi over 4, so that's going to be 2 cosine of pi over 2, that's 0, plus 3 times the cosine, 3 times the sine of pi over 2, which is 1, so we get b for number 9. A particular solution to this equation is in what form? Let's solve our characteristic equation. That'll help us a lot. R to the 4th minus r squared is equal to 0, or r squared times r squared minus 1 is equal to 0. R is equal to 0 with a multiplicity of 2, and r is equal to plus or minus 1. That means our characteristic equation will look like a plus, or I'll use the c's we're used to, c1 plus c2t. That's coming from our 0 with a multiplicity of 2, and then we have c3 e to the negative t plus c4 e to the t. Now, looking at what we have over here, what would we like our guess for y particular of t to be? Well, in a perfect world, it would be a cosine t plus b sine t. Remember, sine and cosine always have to come together when we're guessing like this, plus c e to the negative t plus, and then we have to decompose this 4t into some constant times t plus some constant, so that's not a, dt plus e. Okay, awesome. We have some issues to deal with, though. In order to get rid of the overlap that we have between this component and that component, and also between e to the negative t here and some constant times e to the negative t there, we will have to multiply some things. We'll have to multiply some things by t. But just to make sure that we don't do anything stupid in the end, let's notice that we definitely don't have to multiply cosine and sine by any powers of t. So we can get rid of both b, d, and e. And additionally, we know that we do have to multiply c by a power of t, at least some power of t, so c is also out. And that leaves us with the correct answer, but let's just show that it is correct, because if we multiply this guy by t, we'll no longer have any overlap with this component, and if we multiply this guy by t, well, that's still not good enough, because we still have some constant times t. I should make this a capital E, shouldn't I? Some constant times t, and over here we have some constant times t. So we need to multiply this thing by t squared to get out of all that, so 10 is a. Let's find a particular solution through variation of parameters. So we need to solve for our characteristic solutions, our fundamental solutions, in order to start collecting the terms that we need for variation of parameters. R squared minus 2r plus 1 is equal to 0. R minus 1 squared is equal to 0. Right? Yeah, so r is equal to 1 with a multiplicity of 2. That's fine. That means that our yc is equal to c1 e to the t plus c2 te to the t. Okay, great. Now we can, I'm going to make a list up here. For variation of parameters, we need y1, which is just our first fundamental solution, e to the t. We need y2, that's our second fundamental solution, te to the t. We need f of t, which is this right-hand side here, so long as the coefficient on our y double prime is 1, so that's e to the t over t. And then we need w, which is the Wronskian of these two fundamental solutions. That's the determinant of e to the t and its first derivative, and then te to the t and its first derivative, te to the t and e to the t plus te to the t. So taking this determinant, we have e to the 2t minus, plus t e to the 2t minus t e to the 2t. So we get e to the 2t as our solution. And I'm going to take all this and kind of make it a little small here, because we need some space for this formula. We know that the variation of parameters method says that yp of t is equal to negative y1 times the integral of y2 times f of t over the Wronskian dt plus y2 times the integral of y1 times f of t over the Wronskian dt. So there's at least a little bit of a pattern to it. The real thing to remember is that you do have to include that negative sign. There will always be an answer choice waiting for you if you forget it. So be warned. So we can set this up. Yp of t is equal to negative y1, so negative e to the t times the integral, ooh, that's a snazzy integral, of y2 of t, that's t e to the t, multiplied by f of t, that's e to the t over t, and then our Wronskian is e to the 2t dt. Then we are adding y2, which is t e to the t times the integral of y1 of t, that's e to the t times f of t, that's e to the t over t, and we're dividing by our Wronskian 2, which is e to the 2t dt. So let the cancellations begin. Everything cancels here. We get 1, so this will be a t right there, and then we get 1 over t for this integral, so we get an ln t, like so. So we can rearrange this and say that yp of t is equal to t e to the t ln t minus 1, and then all we have to do to find our general solution is add back in our characteristic solution, which I made really small over there, so it's a little difficult to see, but where is it? Yeah, it's right here. C should be our answer for 11, unless I misread. Yep, we got it. Okay, 12. For this system, x prime equals ax, what is the origin? Well, we know a couple things. And I'm not writing them out because they're like whole sentences. If our eigenvalues are real and positive, our origin will be a, they call it a proper nodal source. See, I'm having to deal with these exact same problems in MA 265, and they use much less technical words for, sources and sinks, etc. So I'm getting a little confused, but we're fine. It's just terminology. Then if both of our eigenvalues are negative, we will have a, or wait, is it improper? I actually don't remember. Feel free to go Google that or look it up. There's a good little My Lab Math table that they give you. Yeah, that would be a good thing to check out. But because proper versus improper, I'm not exactly sure the difference. Okay, but a saddle point is when we have an eigenvalue that's positive and an eigenvalue that's negative. We get a spiral sink if we have a negative real part of our eigenvalue with a complex conjugate bit added on, and then a spiral source when we have a positive real part of our eigenvalue and then a complex conjugate bit too. So let's solve this. This should be pretty fine. Solving the determinant of a minus lambda I equals 0, 5 minus lambda times negative 7 minus lambda plus 40 is equal to 0. So lambda squared plus 2 lambda minus 35 plus 40, so plus 5 is equal to 0. Now that ain't going to factor, so negative b over 2 is negative 1, plus or minus the square root of b squared, so 4 minus 4ac, that's minus 20. 4 minus 20 is negative 16, so 4i over 2i. And we said if we have a negative real part and a complex conjugate part, 2, on our eigenvalue, that means that we will have a spiral sink, because this will contribute to an e to the negative t term, and all this will do will contribute to some sine and cosine rotation factor built in there too. But if you plug in higher and higher values of t, this approaches 0. So overall, this will kind of scale all our values down into the origin as t approaches infinity. So 12 is D. 13, we have a 2 by 2 real matrix with these eigenvalues and corresponding eigenvectors. Let's find the matrix exponential. So if we can find our fundamental matrix phi of t, our matrix exponential is going to be phi of t times phi at 0 inverse. So let's compute these. We know that the fundamental matrix phi of t, I kind of really like writing that phi. It's kind of satisfying. That's going to be composed of lambda 1 times v1 as one column. Sorry, e to the lambda 1 t times v1. So we get 2, 3, but both of those will have e to the negative 2t, e to the negative 2t's on them. And then for lambda 2, we will get 1 e to the 5t and 2 e to the 5t, like that. Then we need our guy evaluated at 0. That's just 2, 3, 1, 2. We need the inverse of this. For that, we need the determinant. That's 4 minus 1. So, 4 minus 3, which is 1. We don't have to do anything. And taking the inverse of a 2 by 2, the other thing we have to do is change the signs on the off-diagonal terms and flip, ooh, wow, that did a lot, flip the main diagonal. So, computing this guy, multiplied by this guy, we should have our matrix exponential. This will be another 2 by 2, although it'll be a little bigger. We'll have 4 e to the negative 2t minus 3 e to the 5t, 6 e to the negative 2t minus 6 e to the 5t minus 2 e to the negative 2t plus 2 e to the 5t and negative 3 e to the negative 2t plus 4 e to the 5t, which is exactly what we have going on over here in C for 13. 14, let x and y be the solution to this initial value problem here. We're finding x at 1. So let's find our solution, where our solution will be in the form x of t is equal to c1 v1 e to the lambda 1t plus c2 v2 e to the lambda 2t. Let's find all of these. Finding our eigenvalues, we're solving the determinant of a minus lambda I equals 0, 3 minus, not 3, but lambda, 5 minus lambda plus 1 is equal to 0. Lambda squared minus 8 lambda plus 15 plus 1 is plus 16 is equal to 0. Oh no, multiple eigenvalues. Lambda minus 4 squared is equal to 0. So lambda is equal to 4 with a multiplicity of 2. Ooh, things just got interesting. So it really won't be in this form at all. It will be in C2. This whole bit's correct, by the way, but we only have one eigenvalue. So C2 v1 times t plus our generalized eigenvector times e to the lambda t. And I'll just go replace these lambdas with 4, because that is our eigenvalue. So let's plug in 4 to a minus lambda I to find our first eigenvector. Not 3. Negative 1, 1, negative 1, 1. We can simplify this down to 1, 1, 0, 0. And since this is saying that x1 is equal to x2, we can move, that's 2x, x2, because we can move this, this guy over to the other side. And x2 is our free variable. We can make a vector out of x2 where this top bit is what x2, let's see, x2 is equal to, oh, I wrote this wrong, didn't I? Negative x2. If we move this over to the other side, there we go. So x2 is equal to negative 1 x1, and it's equal to 1 of itself. So there is our first eigenvector. So we can go up here, replace v1 with negative 1, 1, and also this one. Now to find our generalized eigenvector, what we have to do is solve a minus lambda I set equal to our first eigenvector. So negative 1, negative 1, negative 1, 1, 1, 1. And what we're shooting here, what we're shooting for here is to simplify it down to the point where we have these four components looking the same as we had our entire matrix when we solved for our first eigenvalue. Nope, eigenvector. And once we do, everything on the right, so this vector 1, 0 is our generalized eigenvector. So that's 1, 0. We can go replace that up there. Now, since we have an initial condition here, let's solve away for that. 1, 2 is equal to c1 times negative 1, 1 plus c2 times this component will go to 0 because t is 0 times 1, 0, and this component will go to 1. We can make a matrix out of this. Negative 1, 1, 1, 0, 1, 2, 0, 3, like that. So not x1, c1 is equal to 2, and c2 is equal to 3. Now we are finding x at 1, right up here, where they're calling x the upper half of this system, of this solution system that we found here. So x bar I'm using to represent both of these together. So x of t alone is negative 2 e to the negative 4t, kind of pulling all of this together, plus, sorry, that'll be a minus, plus 3 times negative t plus 1 e to the 4t. So when we plug in, that's not a negative 4t, where'd I get that from? There we go. When we plug in x is equal to, nope, still not x. When t is equal to 1, this whole bit is going to go evaluate to 0 because we'll get 0 in here. So we'll just be left with negative 2 e to the 4. And so 14 should, be A. Number 15, let's find a particular solution to this non-homogeneous linear system. So the thing that makes these questions feel kind of not so good sometimes is when you try to guess too much stuff at once. So what we're going to do is get rid of t1, replace it with t0 and 0, 1, and then we're going to solve this, this whole thing in two steps. One where we kind of close our eyes and pretend that this guy doesn't exist, and one where we close our eyes and pretend that this one doesn't exist. And we'll be able to get the two contributions, the individual contributions made by this component and this component, add them together, and we'll have our solution. So our guess for x particular, ignoring the existence of this thing, for this one will have to be at plus b, and then ct plus d, because remember we have to expand this t into some constant times t plus another constant, but then that also has to potentially be the case on the other line, even though we have a 0 down there in that second row. So if this is xpg, x prime pg of t will be ac. So let's plug this into our equation. AC, that's x prime, is equal to 1, 0, 1, negative 1 times AT plus B, CT plus D, and then we are adding T0 like that. So making this into two individual equations, A is equal to A is equal to AT plus B plus T. Great. We can equate things here, but first off, I'm not actually going to go do that. We're going to go set out our second solution. C is equal to AT plus B minus CT minus D plus 0. So taking a look back up here, what I was about to do is say that we can set our t coefficients equal to each other. So AT is equal to negative t, so A is equal to negative 1. And since A is equal to B, using our constant terms up here, we know that B is also equal to negative 1. Going down here with this knowledge, we can replace this A with a negative 1 and this B with a negative 1. So we have C is equal to negative t minus 1 minus CT minus D. And okay, since we have two t components, we can see that C is equal to negative 1. So I'll put that up here. C equals negative 1. And then as a result, C equals negative 1 minus D. And since C is equal to negative 1, D is equal to 0. D is equal to 0. Okay, great. So we are most of the way done. I'm actually going to get rid of most of this work because I'm mostly sure that we are on the right track with this one. We can replace A with negative 1, B with negative 1, C with negative 1, and D with 0. So that's the contribution from this t component. Now let's pretend it doesn't exist and deal with 0, 1, although that's much easier because our xpg, our guess for x particular, well, this is our second guess really, of t is just AB. And so plugging in that for x prime, well, no, taking its derivative and then plugging it in for x prime, we'll see that 0, 0 is equal to 1, 0, 1, negative 1 times AB plus this vector over here, plus 0, 1. So 0 is equal to A, and 0 is equal to A minus B plus 1. As a result, B is equal to 1, A is equal to 0, so we can add these together and get our x particular, which is just given here. And looking around, E should be our answer for 15. Let's use the Laplace transform to find y of t for this. Oh, reading this during like my actual exam attempt was the scariest thing in the world. And this is a completely terrible, awful question to actually run through. The following linear differential system. So, oh God, we know that x double prime plus y prime is 0, and y double prime plus x prime is 4 sine t. Let's take the Laplace transform of both sides here, knowing that the Laplace transform of y or x double prime, doesn't really matter, is alpha squared y alpha. If this is your first time seeing me use alphas, I really hate writing s's. They look like my 5s. And then I'm not going to write anything else because all of our initial conditions are 0. So originally we would have minus alpha y at 0 minus y prime at 0. But none of that matters here. For our purposes, the Laplace transform of y is just alpha y alpha, and the Laplace transform of, sorry, that's y prime. The Laplace transform of y is y alpha. And those are just little subscripts over there. Okay, using this, we can take the Laplace transform of both of our equations. We will get alpha squared x alpha plus alpha y alpha is equal to 0, and then alpha squared y alpha plus alpha x alpha is equal to 4 over alpha squared plus 1. That's interesting. Let's see, what did I do? What did I do here? Oh, I know what I did. Let's take this equation right here and say that alpha y subscript alpha is equal to negative alpha squared x alpha. Let's divide out an alpha, and there we go. We have a substitution that we can make into this equation here. Although I don't actually want to do it that way. We got to be careful because we're looking for y of t in the end. So instead of doing that substitution, we will rewrite this. We're solving for, we're trying to substitute x in. And so alpha squared x alpha plus alpha y alpha, let's rewrite that like that, and this should be negative. Okay, I hope that's good. This doesn't feel like the substitution I made before, but whatever. So this substitution can be plugged in directly here. So alpha squared y subscript alpha plus alpha times negative 1 over alpha y at alpha is equal to 4 over alpha squared plus 1. These two cancel, we get a negative, and so we can factor out y alpha, and we'll be multiplying this by alpha squared minus 1 for a second, but then dividing that over, and we get 4 over alpha squared plus 1 and alpha squared minus 1. Okay, we're actually good. This is what we should have at this point if I remember my exam. But wait, it gets a whole lot worse. Are you ready for the biggest partial fraction you've ever seen in your life since that awful week in Calc 2? Because we can split this up into a alpha plus b over alpha squared plus 1 plus b alpha plus c over alpha squared minus 1. Am I? Oh yeah, no, I can do even more. Sorry, this alpha squared minus 1 is also factored into alpha plus 1 times alpha minus 1, so we need to do that, but that makes it slightly easier, but now we're dealing with three things. We have c over alpha plus 1 plus d over alpha minus 1. That's a nice looking alpha. I'm liking that. Okay. Calm down. I think we're gonna make it in the end. We have to multiply all of this up into all of that, and just for now, I'm going to pretend like this 4 doesn't exist. We're just going to circle it to remember that it's there, but treat it as a 1. I don't feel like getting dumb values. So, and that's actually a stupid decision on my part. Let me be special. So we're multiplying a alpha plus b by alpha squared, well, we're multiplying it by both of these guys, which we know come out to alpha squared minus 1. So that's useful. And then we're adding c multiplied by alpha squared plus 1 times alpha minus 1. And then we're adding d multiplied by alpha squared plus 1 times alpha plus 1. Let's do some expanding. We will get a alpha cubed minus, oh, I gotta sort this correctly, minus a alpha plus b alpha squared minus b. Okay, then over here we get c alpha cubed minus c alpha squared plus c alpha minus c. And then with our d's, we will get d alpha cubed plus d alpha squared plus d alpha plus d. Okay, and so now I've made this into a nice little form. All of this is equal to, I'll stop being so stupid. Get rid of this. We're using 4, so 4 it is. And really the only thing that we actually care about that's equal to 4 is this guy. Really these guys are equal to 0, 0, 0. And as a result, we can make an ungodly matrix out of this, which will be 1a alpha cubed plus 0 b alpha cubed plus 1c plus 1d is equal to 0. Then we know that 0, 1, negative 1, 1 is equal to 0, negative 1, 0, 1, 1 is equal to 0, and 0, negative 1, 1 is equal to 4. Okay, now, the first time I went through this, assuming we have the correct matrix here, but last time I tried to do this, the first time around, I made a mistake and still ended up logicking it out and getting the right answer, but it was not pretty. So let's simplify this correctly the first time. Let's add row 1 to row 3. That'll give us 0, 2, 2. We can simplify this down to 1, 1 and use it to subtract out those two. That's some good simplification action there. Then what else? What else can we do? Let's add row 4 to row 2. That will give us 0, negative 2, 2, 4, or negative 1, 1, 2. Okay. Now let's add row 3 to row 2. That gives us 0, 2, so we can turn this into a 1, 1, and this into a 0, 3. And now what? Let's flip the signs here and subtract row 3 from row 4. That gives us a 0 and a negative 1. And now let's add row 2 to row 4. That will give us a 0 and a negative 2. And then finally, I think I made my life harder doing it that way. Let's subtract row 2 from row 3. That gives us 0 and negative 1. Okay, assuming that these values are correct, which I think that they are, we see that A, yeah, okay, we're good. A is equal to 0, which is nice. B is equal to negative 2. C is equal to negative 1, and D is equal to 1. And after all that work, we can directly take the inverse Laplace transform of this. We will get negative 2 sine t minus e to the negative t coming from this guy, and then plus e to the t. Yeah, God, hate this problem. Yeah, 16b. Sweet. 17 though, let's find the Laplace transform of something a lot easier in some ways, but you kind of have to do a little more mental gymnastics and less brute force pain. So between t is equal to 0 and t is equal to 1, we want our function to be equal to 0. So I'm not going to really do anything for that, but we'll add a u1 of t, which is the unit step function at 1 of t. So for all t less than 1, our function is equal to 0. It's undefined at 1, down at 0, but it's defined up at 1 for y is equal to 1. And then for all t greater than 1, greater than and equal to 1, our function u1 of t will evaluate to 1. So that's a little crash course on what's going on here. And we're multiplying this by e to the 2t t squared. Okay, so a couple things we can do here. Let's take e to the 2t and put it outside. So we have e to the 2t times u1 of t squared. There we go. And the important thing to recognize is that taking the Laplace transform of anything multiplied by e to the 2t, all that will do if I will need this right here. There we go. All that multiplying anything by e to the ct will do is it will give you the Laplace transform of f of t, but you replace all of your s's, in our case alphas, with alpha minus that c value. So all we have to do at the end is replace alpha with alpha minus 2. And I'm actually going to delete that because we know what to do for it. Now we're left with uc of t, but our function multiplied by uc of t is not in the form that we would like it to be in. So we can do a little messing around with it, and we should get what we want. So in doing this, we can rewrite this as u1 of t, and what we're going to have to do, oh, this is going to suck. Yeah, this will suck. Even though at this point, fun fact, we can actually just find our answer from what we already know now, and that's what I did during the exam, and then made a minor mistake and got it wrong anyway, but whatever. Okay, so we'll have to replace all of our t's with t minus 1, so we'll get t minus 1 squared in here, but then we've done some things that we don't really want to do, so let's expand this. u1 of t multiplied by t squared minus 2t plus t squared minus 2t plus 1. There we go. And yeah, what we're going to have to do is now add outside of this u1 of t times all the multiplied by all the things that we need to put this back to normal. So u1 of t times 2t minus 1. That does it, right? If we add these together, we'll get, yep, 0 and 0. Okay, so I hope you see what I've done here. We can then zip this guy back up into t minus 1 squared, and as long as we add this term, what we have here, even though I'm sorting it very badly and it's kind of hard to see what's going on, I'm going to rewrite this. 2t minus 1. This thing is equal to not this thing. This thing is bad. This thing is equal to this thing right here, because we'll get u1 of t times t squared minus 2t plus 1, and then we will subtract that 1 and add 2t to get rid of those changes. But now, wow, look, we have another problem, that in here, this is not in the form f of t minus c. So we need to split it up again. But really, we're only dealing with this guy, so we can leave him alone. This one's good. So u1 of t at 2t minus 1, we want this to be 2t minus 2, so that we can say that this is 2t minus 1, like that. And what we've done there is subtracted u1. No, we've subtracted 1, so we need to add u1 of u1 of t multiplied by 1, right? Because this will be 2t minus 2, and then we add a 1, and that's our 2t minus 1. Okay, so we've made everybody in this situation happy, we can rewrite f of t as this guy, which is good, u1 of t times t minus 1 squared. And then we have plus u1 of t times 2t minus 1, no squared there, plus u1 of t times 1. Great. Now this is looking scary, and it kind of is, but this is actually a very nice form that we can do a lot of things pretty easily with, because the Laplace transform of uc of t times some function of t minus c just gives us, wait, make sure I'm going on the right line. There we go. Gives us e to the negative cs, so we will get e to the negative alpha, because our c value is 1, and then the Laplace transform of not f of t minus c, but just f of t. So in this case, f of t is t squared, and the Laplace transform of that is 2 over alpha cubed, because I'll just show you the rule. You can go look at it yourself. T to the n Laplace transform is n factorial over s over s to the n plus 1. Okay, so we got that bit. And then over here we have e to the negative alpha, and then the function that we're taking the Laplace transform of is 2t, so that's 2 over alpha squared. And then finally, the Laplace transform of u1 of t times 1, well, that's just going to be e to the negative alpha over alpha, because the Laplace transform of 1 is just 1 over alpha. So here we go. You'd think we're done. We're not done. There isn't actually an answer choice here to catch you if you forgot this step, which is kind of nice of them. But look at our rule up here. Because we're multiplying everything by e to the 2t, we have to replace all of our t's, all of our alphas with alpha minus 2's. So all of these alphas are getting replaced with alpha minus 2's, and then is that, yeah, that should be it. So let's factor out an e to the negative alpha and replace that alpha with alpha minus 2, so we'll get negative alpha plus 2 over there, and they're very kind to have only one option with e to the negative alpha plus 2, but then we factored that out. We can get rid of all these, and we'll have alpha minus 2 squared, and alpha minus 2 cubed. Awesome. So 17 is e. There's something super duper satisfying about that working out. I'm not really sure what it is, but I like it. Let's find the Laplace transform of t e to the t cosine 2t. So we know multiplying anything by e to the t, all we'll do at the end is replace alpha with alpha minus e to the what power? Let's see. Got to make sure I'm not messing that up. Yeah. Minus 1. Got it. Careful. And so now we're just taking the Laplace transform of t cosine 2t, and we will deal with this at the very end. This stumped me. I forgot that this was a thing, this final rule down here that says that negative t to the n times f of t is the nth derivative of f of s. So, since we are multiplying negative t to the first power by cosine of 2t, we will get negative f prime of alpha, where we're taking the Laplace transform of cosine of 2t and taking the negative derivative of that. So the Laplace transform of cosine of 2t will just be alpha over alpha squared plus 4. The derivative of this will be, we'll have to go all the way back to Calc 1, do some quotient rule. That will be 1 times alpha squared plus 4, and then from that we're subtracting the derivative of the bottom times the top, so alpha times 2 alpha, and then we're dividing by the bottom squared. Alpha squared plus 4 squared. And then we remember that we're finding the negative derivative, so we can flip the signs over here. We get 2 alpha squared minus 4, so we get alpha squared minus 4. I think I may have already messed up. Interesting. Let's hope that I did not. Yeah, no, I don't think I did. Okay, don't listen to me. Don't listen to me at all. Okay, this is looking good. We have to remember, at the very end, we were replacing alphas with alpha minus 1s. So this numerator, so we're applying that. This numerator will become alpha minus 1 squared, so alpha squared minus 2 alpha plus 1 minus 4 is minus 3 over, let's see, alpha squared minus 2 alpha plus 1 plus 4 is plus 5. Okay, and that lands us on our correct answer, question mark? No, negative 3. There we go. Negative 3 on the numerator is correct, so 18 should be C. 19, let's find the solution to this initial value problem. Since our initial conditions are both equal to 1, our Laplace transforms of our left side are a little yuckier than usual, so we will get alpha squared y subscript alpha minus alpha times y at 0, which is 1, minus y prime at 0, which is minus 1, plus 4 alpha y alpha. We're taking the Laplace transform of 4y prime. 4 alpha y alpha minus y at 0, so minus 1 plus 3 y at alpha. Okay, there's our left side. What about the right side? Well, the convolution of f and g, this is our convolution theorem. This tells us that the Laplace transform will just be the what's it called? The Laplace transform of f times g multiplied together. So in our case, f of t is just what they have in here, where all of the t's are t minus taus. So we can say that f is equal to the hyperbolic sine of t, and g is the cosine of t. So let's find these. Well, the cosine of t is just going to be alpha over alpha squared plus 1. Find their Laplace transforms. That's what I was trying to say. And then the Laplace transform of hyperbolic sine will just be a, which is 1 in our case. So 1, we're multiplying these, sorry, by the convolution theorem. 1 over alpha squared minus 1. Okay. So multiplying these together, we'll get alpha over alpha squared plus 1 multiplied by alpha squared minus 1, which is alpha to the 4th minus 1, although I don't know if we want to actually do that. We may have to do some, yeah, I'll just leave it as alpha squared plus 1, alpha squared minus 1 for now. And so since this is equal to all of this stuff over here, I'm going to add the alpha and the negative 2 over to the other side, and we will get alpha squared y alpha plus 4 alpha y alpha plus 3 y alpha is equal to alpha over alpha squared plus 1 times alpha squared minus 1, and then what else? What else do we have? Plus 2, and then plus alpha. Okay, so what do we have to deal with here? Okay, this is actually great. I didn't realize this ahead of time. I should have read the question. We're just finding the Laplace transform of y of t. I'm sure you saw that. It's 11:40. I've been doing so many of these today that I've lost track. So if we factor out everything multiplied by a y of alpha, we can say that y of alpha is equal to 1 over all that stuff, so alpha squared plus 4 alpha plus 3, and then multiply that by alpha over alpha to the 4th minus 1, which seems to be the form they have it in for the solution. And I shouldn't be so quick to circle that because, oh, look at that mistake. I caught that. Look at that mistake right there. Let's see, I think I did this before too. Okay, when we were taking the Laplace transform of 4y prime, what we did was said 4 alpha y alpha, which is correct, but then it should have been minus 4 y at 0. So this is minus 4, so we end up with a plus 5 over here, not a plus 2. So we have plus 5 over nothing, actually, plus 5 and then plus alpha. And this should be our solution, right? Nope, that's minus s minus 5. It's getting real late. Good thing we only have one question left. So 19 is A. Finally, the last question that I have to do for this subject before I start MA 303 in like 6 weeks. Oh, God. Okay, x of t is the solution to this initial value problem. Let's figure it out. Since all of our initial conditions are 0, we can just say alpha squared y at alpha plus no initial condition terms, except that we're not dealing with x, we're dealing with... Okay, I'm actually going to quickly restart this and explicitly use y instead of x because my x alphas and alphas look too similar. So we will have alpha squared y alpha plus 2 alpha y alpha plus 10 y alpha is equal to e to the negative 5 alpha. And I'm getting that from delta at t minus c is e to the negative cs. So we can say that y alpha is equal to e to the 5 alpha times 1 over alpha squared plus 2 alpha plus 10. Can we write that in a nicer way? I think we can. Oh yeah, look at that. We can write that as, so I'll be clear, we have alpha squared plus 2 alpha plus 10 over here when we divide out all of the things on y alpha over there, but we can write this in a much nicer way, and there's a hint that we don't have to do any partial fractions from the fact that all of our solutions, all of our options for solutions only have one component. So we can rewrite this as alpha plus 1 squared plus 3 squared. And then if we go up top here and multiply this by 3 and 1/3 on the outside, now this is exactly in the form that we want it to be for e to the at sine bt. Perfect, where a is -1 in our case. So we do have to deal with one extra thing though, because we have e to the negative cs multiplied by the Laplace transform of some f of t, and we have to recognize that on the whole what we'll be doing here is seeing that y of t is equal to uc of t, where c is 5 in this case. And sorry, this is a -5. That's a stupid mistake on my part. Whatever you have subtracted in this always ends up being subtracted in your Laplace transform for that delta function. So we have u5 of t multiplied by the inverse Laplace transform of this thing, where we replace all of our t's with t minus c's. So that will be e to the negative t, but we replace that t with a t minus 5 sine 3 t minus 5, and then we can't forget the 1/3 we had hanging out over there. So it's not a cosine. We can get rid of those three, and this answer choice forgot to replace that negative t with a negative t plus 5. So this answer choice D matches what we have exactly. 20 is D. Okay, this was a little sloppy at the end, and I apologize if you felt the same way. If you have any questions about any of this, comment please. But yeah, this is kind of crazy. I'm done with DiffEq. Well, before the final, I'm done with all my recordings, which means I got to go do something like 15 or 17 videos for linear. That'll be fun. But thanks for joining me, and hopefully this was helpful. This is definitely the hardest past exam, that is for sure.